Okay, Dijkstra's algorithm, as we have seen, can be used to find shortest paths from a vertex to all the others. But that's not the only use for Dijkstra's algorithm. I mean, in the sense that you can define the cost as a much more general concept, apart from, let's say, a concept of distance, let's say, in an actual path. So in a usual sense, it would be an additive cost. So to get to, let's say, B, you go to A. To get to A, you need to get to E, for instance. And the cost to get to B is the sum of the costs between E and A and the cost from A and B, for instance. But that's not the most general scenario. That's valid when you define the cost as the distance. Or consider this scenario where in a communication network, for instance, you would like to travel the path that has the best bandwidth or the best capacity. Suppose that you have two alternative paths from your source to destination. Let's say this is relay 1 and this is relay 2. And you have the links in this graph. Now, if we were doing minimum cost paths, let's say the cost to on this edge is 1 and this is 2, and the cost on this edge is 1 and this is 1, you would prefer the path through R2 because that is the minimum cost. From S to D, the cost through R1 is 3, the cost through R2 is 1. 2. Therefore, you prefer it. However, suppose that these weights do not represent the costs, but the capacity of the links. In this case, you would like to go through R1, because if you go through R2, the capacity you will be able to use is 1. But if you go through R1, there's a capacity of 2 here. Well, in fact, these two paths are in general equivalent, because when considering bandwidth or capacity, you will look at the minimum across the entire path, because that will be your effective capacity throughout the entire path. Because even if you have capacity of 2 here, you will not be able to use that entire capacity because you will have a capacity of 1 here. But let's change the numbers and make this a non-trivial example. Let's say the capacity here is 3, the capacity here is 5, and the capacity here is 2, the capacity here is 6. Now, in this case, the capacity of the entire path from S to D through R1 is 2. Because even if you do have an edge of capacity 6 here, your communication is going to go through this edge, this connection from S to relay 1, source to relay 1, and that has a capacity of 2. So you will not be able to make use of that capacity of 6 in the next hop. However, when you look at the path from source to destination through R2, you see the capacity on the entire path is now 3. Because, well, you do have an edge here with a capacity of 5. But since this is the minimum, the capacity with 3, that will determine the capacity of the entire path. So what you are looking for in this scenario is to maximize the minimum capacity along any path. You can also do this using Dijkstra's algorithm. Let me erase all these. But in order to be able to do that, you need to define your weights and the operation you perform on them to determine the entire cost of a path. You have to select them carefully. And what we call those type of structures are cost algebras, because the weights may not be additive. In a minimum path, a minimum cost path, or a shortest path, the weights are additive because you compute the total cost of a path by adding the costs. But in the capacity problem, it was different. Therefore, we define a cost algebra, which consists of a set A, an operation star, an order, and an identity. So set A, along with the operation star and with the identity element 1, is a monoid. If you recall what a monoid is, let me remind you. A is a set, and the operation star defined from the Cartesian product of A with itself to the set A is closed, and it's associative, and it has the identity 1. So when you have this structure, we call this a monoid. Okay, so it's not a group because it may not have inverses. And we have a total order defined on the elements of the set of A, and 1 is the minimum element according to that total order. And final condition is A is called isotope with respect to operation star. And this means, well, from if you have taken calculus courses, this is analogous to what we know as monotonous functions. So monotonous increasing, monotonous decreasing, or non-decreasing, non-increasing, etc. So this is defined mathematically as when you have these 3 elements in set A, if A is less than or equal to B, this should imply when you compute this operation, A, let's say star C, should also be less than or equal to B star C, and it should also be the other way around. C star A less than or equal to C star B. So from both right and left applications of this operation, this order has to be preserved. Now, addition obviously satisfies this, but there are other operations that satisfy this isotonicity property, and some examples are given here. But this is the usual example we have seen earlier, the cost or delay. Set A here is the set of positive real numbers along with positive infinity. The operation is addition. The total order is, well, less than or equal to the usual order, and the minimum element is 0. In the capacity problem, you have again the same set, but now the operation is not addition, but the minimum operator. Okay, so the result of the operation gives you not the sum, but the minimum of the 2 elements. And now the total order is greater than or equal to. It goes the other way around. And therefore, the minimum element is plus infinity. Well, it's not the minimum as we know it, but it satisfies this for all A values because the operation here, or the order here, is greater than or equal to. Okay, so since this is really a cost algebra, you can apply Dijkstra's algorithm to solve this problem also. Another example is availability or resilience in terms of probability. For instance, you have assigned probabilities to each link in a communication network so that that probability indicates the probability of, let's say, a communication packet correctly delivered over that channel. Okay, so that's a probabilistic system. And you assign values between 0 and 1 because that's what that's the set of values a probability can take. And now your operation is not addition, it's not minimum, but it's multiplication. If you define the probabilities as probability of correct transmission, the probability of the correct transmission from the source to the destination is going to be the product of all those probabilities along the way. Okay, again, the order is greater than or equal to because you want to maximize this probability now, not minimize it. And the minimum value in this case, minimum in the sense that it satisfies this for all A, is 1. A similar cost algebra can be defined as a Boolean availability. So the probability now here is reduced to zeros or ones. Okay, so Dijkstra's algorithm can be applied to a variety of scenarios in this setting. And one final point is the A-star search algorithm. It's a famous algorithm, a very widely used algorithm in artificial intelligence or robotics. It's the extension of Dijkstra's algorithm where you use a heuristic value for the cost from each vertex to the destination and add that cost to each vertex. So if you select this heuristic value to be 0, this algorithm boils down to Dijkstra's algorithm, but you have, this is a more general algorithm from Dijkstra. Essentially what you do is, here in this scenario, you have this updated by heuristic values in both sides, but of course this is, you have u here, this is, you have v here, so you have a certain idea of the cost of the remaining path, and you add that to your cost at each iteration. So this is widely used in robotic path planning algorithms, maze solvers, and very similar artificial intelligence applications.